So sometimes you might be asked for the direction or angle of a projectile going through a trajectory. So here I'm going to show you how to calculate it. So we have a projectile launched at 5 meters per second at 45 degrees from the ground. So the full path is that it goes up and it lands again on the ground, making it an even trajectory, an even projectile, so that we can use our standard range and hang time formulas. But the question we're trying to answer is, what is the direction of the path 5/8 through the entire trajectory? So that's just to make it a little more interesting. I mean, you know, halfway through these are even and symmetric, so this must be halfway through. So 5/8 must be around here somewhere. So the question is, what direction is it traveling when it's right there? Because as we mentioned in class, the direction of a trajectory is based on the velocity vector, not the position or the acceleration. Okay, so the first thing we need to know is when this happens exactly. So what we're going to do is, well, we need to know when it happens, because our general strategy, let me cover that first. Our general strategy is to say there's a velocity vector at this point. And to get the direction of that velocity vector, we need its components. To get its components, we need to know when it happens. So the first step is to get the time. So what we're going to do is use our standard even trajectory formulas to get the hang time, the time of the entire path. And then we'll just multiply it by 5/8. So you look up your T hang, I like to call it hang time, because I'm such a sports nut, and it's 2 V naught sine theta over G. We derived it in class. It's okay just to use the formula in this case. There you go. So we plug in 2 V naught means the speed, the 5 meters per second squared. Sine of the angle is 45 degrees. And then over 9.8. Not using a negative number because this is a formula for a time we've derived. The negative was taken care of before. Just put the magnitude of the gravitational acceleration there. And you will get 0.72 seconds. So that's the time to go all the way across. We want 5/8 of the time. So I'm going to say T, now T is the time we're interested in. The time that happens is 5/8 times 0.72 seconds, which is 0.45 seconds. So that's when this happens. Okay. So now we just got to think about how the kinematics evolve and what's happening in 0.45 seconds. And there are 3 kinematics equations that you ever use. There's how the position evolves in time, there's how the velocity evolves in time, and then there's where you combine them to get what happens when you have acceleration for a distance. So here we have the time, 0.45 seconds. So it's one of those first two, but we care about velocity components. So it's that second one I said. We want to think about how does the x component of the velocity evolve over time. Well, Vx is Vx naught plus acceleration dx times time. And for y, Vy is Vy naught plus acceleration of the y times time. You don't even have to memorize this separate. If you took your position evolution equation, y equals y naught plus Vy naught t plus 1 of ayt squared, you could just take a derivative and get to this. It's really just calculus. Anyway, let's look at this and see if we can get these two components. So Vx naught is the initial, right? So it's 5 times the sine of 45, 5 meters per second. Oh, x is the cosine. For 45, they're the same. Plus 0. It's not accelerating in the x. It's just moving in the x. So the x component comes out to be 3.536 meters per second. Y is slightly more complicated. Vy is just 5 times the sine of 45. That's to get the vertical component of the motion. And it is going to evolve in time because it is accelerated. The y is accelerating at negative 9.8. And for how long? 0.45 seconds. Sorry about that. And that's 9.8 times 0.45. So minus 9.8 times 0.45. It turns out this value this negative value is bigger than this positive value. So it leaves you with a negative y component of the velocity of negative 0.875. And that is what you would expect because it is past the halfway point of the trajectory. So the x component just remains constant. That's what it was in the beginning. And the y component you would expect to be negative. The number is negative, sure enough. Let's go ahead and draw it right here, negative. All right, so this was 3.536, and this is negative 0.875. Okay. I drew it that way to help you see the angle. Right? If you're not infinitely familiar with what trigonometric function to use next, let's say, well, the angle here looks like that, or the angle to the trajectory, or I'm sorry, the angle to the trajectory is here. It's what angle is it relative to the x-axis, or the standard definition of a polar angle is what is it relative to the horizontal. So the velocity vector we care about is here. Here is the horizontal, so there's the angle we want. And I went ahead and drew Vy over here to make a right triangle. So you can see there's the right triangle. So we have the opposite and the adjacent sides of the triangle, so we're going to use tangent. Tangent of that angle is TOA, opposite over adjacent. So negative 0.875 over 3.536. And that comes out to negative 0.247, about, depends on how you round. And you take the inverse tangent and you get about negative 13.9 degrees. So we look at that and we say, is that about right? Yeah, that's about right. Once you're a little bit past halfway, you're going to have a small negative angle that will just grow as you go down. So negative 13.9 seems reasonable when you're just a little bit past halfway through the trajectory. Had we solved it for this point, we should have gotten 0. Because at this point, the y component is 0, it's all horizontal. And also I'll say that in general, when you're finding the angle of a trajectory, it's pretty much always this tangent. It's always tangent because you always have Vy and Vx. Now if you go defining it some weird way, not relative to the horizontal, you might have Vx over Vy. But the normal definition, you can see what happened here is what always happens when you're asked to get the direction or angle, is you're going to have to take an inverse tangent somewhere.